everybody. I wanted to clear up one point which I don't think is discussed in the text, but which is kind of interesting, which has to do with the relationship between the orthogonal group, which is all orthogonal matrices, and the special orthogonal group, which are the orthogonal matrices with determinant 1. And as we showed, the special orthogonal group, the matrices have determinant plus or minus 1, so the special orthogonal group is of index 2 in there. And what does this sign of the determinant mean, since orthogonal groups have so much to do with geometry? And so to explain that, I just want to take a little bit of a detour into the notion of frames and orientation. So a frame in Rn is an ordered orthonormal basis. So it's not just an orthonormal basis, but the order of the elements matters. So an example of a frame in R3 would be I, J, K in the usual multivariate calculus notation, where I is I guess 1, 0, 0, and J is 0, 1, 0, and K is 0, 0, 1. And J, I, K would be a different frame. It's the same orthonormal basis, but they're in a different order, so they count as a different frame. Now, if you have a frame, so you have an orthonormal basis in order, you can make a matrix. And the matrix you can make has columns given by the vectors, but in the order that they're given. So you would take your vector u1, and that'd be your first column of your matrix, and u2 and u3 and so forth out to un. And as we've seen, a matrix whose columns are orthonormal vectors is an orthogonal matrix, and its determinant has to be plus or minus 1. And we're going to say that the frame is positively oriented if its determinant is 1, and negatively oriented if its determinant is minus 1. So in the case of I, J, and K, if we take I, J, and K, the corresponding matrix is just the identity matrix. And the determinant of that is 1. So I, J, and K in that order are positively oriented. But if we switch J and I, then we get the matrix 0, 1, 0, 1, 0, 0, 0, 0, 1. And if you compute the determinant of this matrix, you get minus 1. In fact, if you switch the rows or columns of a matrix, it's going to change the sign of the determinant. That's one of the key properties of the determinant. So here you can either think of this as switching the first two rows or switching the first two columns, and so the sign changes. Now, just as a little bit of a hint of what's happening here, we made a transposition of the columns and we changed the sign of the determinant. And as you remember, there are some cases where doing a transposition changes the parity of something, and we're going to come back to that in a minute. So J, I, and K is negatively oriented, but I, J, and K is positively oriented. But you can do this for any orthonormal basis. So if you remember from vector calculus, there's this notion of a right-handed coordinate system. And one way to think about that is in terms of the cross product, which we haven't talked about at all. And the cross product is not really a product in the sense of group theory, because it's actually not associative, but it is useful. And the business with right-handedness is that if you have three vectors in R3, which are orthonormal, when you take the cross product of u1 and u2, so first of all, the order matters. So here I'm looking, or maybe let's do it this way. We take the cross product of u1 and u2. The vector that you get from the cross product is perpendicular to the other two vectors, but there's two possibilities, right? Because if you switch the order of u2 and u1, you switch the direction the vector points. And you say that a system is right-handed, or is if you look at the three things u1, u2, and u3, if u2 cross u3 points in the u1 direction, then that's called a right-handed system. And that's the same as saying, since these are orthonormal vectors, that u1 dotted u2 cross u3 is 1. And this right here is called the triple product. And maybe you looked at this in multivariate calculus, but you can compute it by making the derivative. You make a matrix, you're using the rows instead of the columns, but well, you can do it either way. But you would make a matrix whose rows are u1, u2, and u3, and you would take the determinant of that matrix, and what we're saying is the determinant of that matrix should be plus 1. So positively, in 3 dimensions, positively oriented is the same as a right-handed coordinate system. What about in R2? Well, in R2, the condition is that your two vectors, if you in the order v1, v2, if you take their cross product, it has to point up in the direction of the k. And what that basically means is that, so positively oriented in R2 means that, what's a better way to do this? Here's I and here's j. If you give me two vectors u1 and u2, they're positively oriented if you can rotate ij into them, preserving the order. So I goes to u1, j goes to u2. Notice that if we switched u1 and u2, here's I and j in the plane, if I put u2 here and u1 there, I can rotate the system to get I to u2 and j to u1, but I can't get I to u1 and j to u2 without a reflection. If I were to rotate I to u2 and j to u1 and then reflect, I can get them into the right order. So there's sort of, in the plane, if you keep track of the order, there's sort of two different things that can happen. You can have sort of the first vector is a rotated version of I and the second is a rotated version of j. That's positively oriented, or they could be the other way around. They could be flipped. And the difference between SON and ON is that SON, if you start with an oriented frame, so you start with a right-handed coordinate system, and you apply a transformation from SON, you're going to stay with a positively oriented frame. And to see this, let's suppose we have a frame. So we have U1 up to UN are orthonormal. And let's suppose that A is in SON. So let's make the matrix whose columns are U1, U2, down to UN. And let's multiply that times the matrix A. What do we get? Well, we get a matrix. If you think about the way matrix multiplication works, we get a matrix whose columns are AU1 out to AUN. And the determinant of this, call this U. So then the determinant of A times U is the determinant of A times the determinant of U. But the determinant of A, since A is in SON, is 1. So this is equal to the determinant of U. So if the original frame was positively oriented and you apply an element of SON, the new frame is positively oriented. If you apply an element in ON, which has determinant -1, then the frame reverses orientation. So even in n-dimensional space, there's a kind of a notion of right-handedness. It's a little bit hard to describe in terms of hands unless you can somehow make your hand have fingers that point in 4 independent directions. But this definition using the determinant gives you a notion of orientation. And there are orthogonal transformations like reflections, which mess up the orientation. And then there are orthogonal transformations like rotations, which preserve it. And SON is the subgroup of all orthogonal transformations which preserve this orientation. Now, there's a connection between what we've talked about with regard to permutations, because one kind of orthogonal transformation is just a permutation. So let's look at our original basis vectors, E1 up to En. So if you like, these are the higher dimensional versions of I, J, and K. And suppose we take a permutation in Sn And we think of it as rearranging the basis vectors. So I won't give, maybe the fancy way of saying this would be that sigma takes EI to E sigma of I. The way to think of that is that, right, sigma acts on the indices 1 up to n. And so, for instance, if sigma were the transposition 1, 2, then sigma of E1 is E sigma of 1, which is E2, and sigma of E2 is E sigma of 2, which is E1. So sigma permutes these vectors. And this is a linear transformation, because if you rearrange the basis of a vector space, that's a linear map. And in fact, what is the linear map? Well, the way you figure it out is you work out this formula. And so then this gives you the columns of the sigma matrix, which I'm calling T sigma. So instead of having columns E1 up to En, it has columns E sigma of 1, E sigma of 2, E sigma of n. So maybe just for fun, suppose I take sigma to, let's suppose I take n equals 4, and I take sigma to be the 3 cycle 1, 2, 3. So that means that sigma of E1 is E2, sigma of E2 is E3, sigma of E3 is E1, and sigma of E4 is E4. And the corresponding matrix has E2 as its first column, E3 as its second column, E1 as its third column, because sigma of E3 is E1, and E4, which is last column. So these are called permutation matrices. They're matrices, all of which just have a single 1 in each column and a single 1 in each row, and they're otherwise 0. And one can show that the map, if you define, here I'm going to make a little space here. You say that M is a permutation matrix if it has only zeros and ones with exactly 1, 1 in each row and column. And the first observation is that this matrix is orthogonal. And that's because it preserves the lengths of the vectors, or if you like, the reason it preserves the length of a vector is because if you apply T sigma to a vector, it rearranges the coefficients, but it doesn't change them. So the norm, which is the sum of the squares of the coefficients, doesn't change. And this map from sigma to T sigma is actually a homomorphism from the symmetric group into the orthogonal group. So this is a map F, which takes you from the symmetric group to the orthogonal group. And the reason it's a homomorphism is because sigma 1, sigma 2 is, by definition, the composition of the maps. First do sigma 2, then do sigma 1. And the composition corresponds to matrix multiplication. So T sigma 1, sigma 2 is T sigma 1 composed with T sigma 2. And that's what it means to be a homomorphism. Maybe if we wanted to be a little bit more careful, we would show that, T sigma 1, sigma 2 of EI is E sigma 1, sigma 2 of I, which is, and then if we do T sigma 1 composed with T sigma 2 of EI, this would be T sigma 1 of E sigma 2 of I, which by definition is E sigma 1 of sigma 2 of I, which is E sigma 1 sigma 2 of I. So that's very formal. You can ponder that if you like, but it's basically, or you can just check with a few permutations and see that, that this works out. And the point of all this discussion is the following proposition. So we have a homomorphism that takes a permutation and makes a matrix of it, an orthogonal matrix. And if we take the composition of that with the determinant, that is to say, we take the determinant of f of sigma, we get plus or minus 1. So we have a homomorphism from the symmetric group to plus or minus 1. And that's a fancy way of making the sign of a permutation. And the proof of this is that if you take a transposition, if sigma is a transposition, then T sigma is the identity with two columns switched. And so it has determinant minus 1. And if sigma is a product of transpositions, then the determinant of T sigma is the determinant of T sigma 1 up to sigma m, which is the determinant of T sigma 1 times the determinant of T sigma n, which is minus 1 to the n, because each of those transpositions, you get the determinant is minus 1. And that's the sign of the permutation. It's the minus 1 to the power of the number of transpositions that you need to do it. And the nice thing about this is, having done it this way, any question about whether this is well defined is sort of automatically taken care of. Remember we had to worry that, at least we had to worry a little bit, that if you wrote a permutation as a product of transpositions, that then there was, if it was either even or odd, no matter how much, you could do it in different ways, but you always had either an even number of permutations or an odd number of permutations. We didn't have to use that here. We just had to use the fact that that the determinant is multiplicative. And that's more or less what takes care of that. So the difference between special orthogonal groups, the special orthogonal group and the orthogonal group, is whether or not it preserves the order of the, it preserves the sign of the permutation that has rearranged the basis vectors. Okay.